All right, today's video's lecture is going to, again, review the key concepts from the last lecture to make sure everybody's got everything straight, to understand the trends in these properties. But also there's a couple of other levels of explanation on a couple of these concepts I want to go into greater detail. This is where we kind of break away from regulars and go into more of an honors chemistry level explanation to understand some of these chemical phenomenon that we see when we look at these properties in more detail and depth. All right, first of all, from the last lecture, key takeaways is this. Coulombic attraction is the attraction between the nucleus, which is positively charged, and specifically the valence electrons, because it's the valence electrons that dictates chemical behavior and reactivity for elements. So how much attraction is there between the nucleus and the valence electrons? There are three variables to consider, and that's what the Pogel activity did the week before. First of all, the charge of the nucleus. As we put more protons in the nucleus, think of the nucleus as a magnet. The more protons in the nucleus, the stronger the magnetic pull of the nucleus, and therefore that causes an increase in Coulombic attraction. It's a direct relationship. More protons equals greater Coulombic attraction. Second variable, distance. If the electrons are placed in energy levels farther and farther from the nucleus, think of the Bohr model of the atom. If the electrons are in energy levels, rings, further from the nucleus, the distance between the nucleus and the valence electrons is increasing, and the Coulombic attraction decreases. Greater distance, less attraction between the particles. Now, if we were to compare A and B directly, add an increase of number of protons compared to distance, we find out that the distance is a much bigger effect than the number of protons. So if there's a change in the distance, that will always trump the nuclear charge. Okay? So when we go down a family, distance is the primary factor, okay, in determining Coulombic attraction. Lastly, there's a secondary factor that decreases Coulombic attraction, and that's the number of inner shell electrons. Electrons in between the nucleus and the valence electrons, they repel the valence electrons, and that also decreases the Coulombic attraction. So when we go down a family, there are more and more inner shell electrons, and that causes a decrease in Coulombic attraction. Okay? All right, so when we go down a group, and again, whenever we talk about a group trend, we're talking about going top down on the periodic table. And when we go top down on the periodic table, there are more protons in the nucleus. So factor A is increasing, okay? Factor B is increasing, and factor C is increasing. All three of them are increasing when we go down family. There are more protons in the nucleus. However, the distance is greater, and the number of inner shell electrons is greater. And these two variables outweigh the factor of the number of protons. The distance, since it's growing by going down a family and they're in higher and higher energy levels, that truly will trump A by itself. But also you have the secondary factor of the inner shell electrons. There are more inner shell electrons between the nucleus, which is going to cause a greater repulsion and also a decrease in Coulombic attraction. So down a family, when I go down a family, Coulombic attraction gets smaller and smaller. There is less attraction of the valence electrons to the nucleus when I go down a family because the valence electrons are farther and farther from the nucleus. In a period, we always look at going across the period. So for example, going from lithium all the way to neon. When we go across the period, factor A is increasing. There are more protons, which cause a greater Coulombic attraction. B, there is very little change to the distance between the valence electrons and the nucleus. There's a small change, but not a very big one, because when we add electrons across the period, we're placing them in the same energy level. We're not putting them in a ring farther from the nucleus. There's a slight growth due to electron repulsion that does occur, but not a significant change. And C, when I go across the period, there is no change to the number of inner shell electrons because I'm putting electrons in the valence row. I'm not adding any electrons to the inner shells. And because of that, the primary variable that does change significantly is the nuclear charge. The nucleus has got more protons in it, and that causes Coulombic attraction to increase across the period. So Coulombic attraction increases across a period it decreases going down. Once you know that, you should be able to explain all of the different properties that we talked about, specifically atomic radius, the volume of an atom, how big it is, not mass-wise, but sheer volume-wise, the ionization energy, how much energy it takes to remove an electron, and also electronegativity. How easily does the atom like to gain electrons from other elements? Okay? So atomic radius, when there's an increase in coulombic attraction, there is a decrease in atomic radius. When there's an increase in coulombic attraction, there is an increase in ionization energy. If there's a greater attraction of the electron, valence electron to the nucleus, it takes more energy to ionize it. There's an increase of it. Same thing for electronegativity. So the only variable that is not a direct relationship is atomic radius. Atomic radius is the oddball. If there's a greater attraction, there's a decrease in size because of the greater attraction. All right? So when we go down a group, when we go down a family, coulombic attraction decreases. And therefore, if I go down a family, since there's a decrease in coulombic attraction, there's a decrease in ionization energy, so it's easier and easier to ionize the bigger elements. When I go down a family, they get bigger, it's easier to ionize. The size of the particle gets bigger. The atomic radius get larger because the valence electrons are farther from the nucleus. They're in a higher energy level. There's an increase in the tendency of the ion to form positive ions. Because they are larger and they have a lower ionization energy, they're much more willing to lose electrons than gain electrons, and therefore there is a decrease in electronegativity. They're much more likely to lose electrons than they are to gain electrons, and electronegativity is looking at gaining electrons, not losing. So when I go down a family, elements down in the bottom parts of the period tend to be what we say they're more metallic. More metallic means metals have a tendency to lose electrons. And they're much more likely to lose electrons when you are bigger and you have a lower coulombic attraction. So metals become more and more metallic as we go down a family. When we go across the period, and again, across means going left to right across the periodic table, going across the periodic table, the coulombic attraction increases, which causes the atoms to get smaller. Okay? Atoms get smaller when I go across the period. Even though I'm putting more electrons, protons, and neutrons in the atom, it gets smaller because the nucleus, the number of protons, cause a greater attraction, and therefore the electrons are pulled closer into the nucleus. Because they are more strongly attracted to the nucleus, they have higher ionization energy. You're much more able to easily ionize an element on the left than you are on the right. The further we get to the right, the more and more difficult it becomes to ionize an element. It takes more energy to rip off the electron. Okay? And because of that, it has higher electronegativity values. When I go across the periodic table, the ionization energies increase, but also the electronegativity values increase because the atom is much more willing to gain more electrons because of the greater coulombic attraction. And therefore, when we go across the period, elements become more non-metallic. Non-metals have a tendency to want to gain electrons. Therefore, they have high electronegativities. Metals want to lose electrons, and they tend to have low electronegativities. Okay? So let's look at these questions, see if you can answer them. What element would be the most likely to become a positive ion? Which element? Which element would be most likely to want to form a positive ion? And therefore, we're looking at losing electrons, and an element that has an affinity to lose electrons is going to have a low, or in this case, the lowest ionization energy. Well, based on the trends of ionization energy, going across, ionization energies increase. Going down, ionization energies decrease. Which element has got the lowest ionization energy? If you know the trends, you should be able to identify which element has the lowest ionization energy. Hopefully you picked right here, the element in the bottom left-hand corner. That element has the lowest ionization energy. And if you don't trust me, look it up. But that element has the lowest ionization energy. And which element is that? Fr. Francium. Francium is the element that is most likely to become a positive ion. because it has the lowest ionization energy, it has the lowest coulombic attraction, and therefore its valence electrons are much easier to be lost. What element would be the most likely to become a negative ion? Now I know what some of you put down. You said right away helium. Why would helium not want to be a negative ion? Now helium has got the greatest coulombic attraction value of all the elements. But there's a second dynamic you have to consider here. While it has the greatest coulombic attraction, it does not want to form negative ions. Why? Its valence electrons are already full. So when we look at ionization energies and electronegativities, we want to cross out the noble gases because they're already full shells. Now, helium and the noble gases tend to have very high coulombic attractions, but when it comes to looking at reactivity of electrons, they have no reactivity because of the full shells. So what element now is in the upper right-hand corner if we get rid of group 18? And the answer is fluorine. Fluorine is the element that is most likely to become a negative ion. Fluorine has got the highest electronegativity, and it has a value assigned to it of 4.0. 4 is the largest you can get on an electronegativity scale, and fluorine is the only element that has it. Based on that, what element is the most metallic in character? Which is the element that's most likely to lose electrons? Francium. Most nonmetallic? Fluorine. So, elements in the upper right-hand corner, as long as we get rid of the noble gases, these tend to have very high non-metallic character. They like to be nonmetals, which makes sense because if we look at that staircase that cuts through, the elements that are to the right of staircase are in this corner. This is the location of the nonmetals. Elements to the the left of the staircase are metals, and specifically the elements over in the left-hand corner tend to be the most metallic because they tend to lose electrons the most easily. Okay? A couple other concepts that I want to just wrap up on ionization energy. The first is up above you have a table. Take a second to look at these values. These are the ionization energies of what we call successive ionizations. So for sodium, the first ionization energy is the amount of energy it takes to remove the first electron from sodium. So if I look at sodium, 1s2, 2s2, 2p6, 3s1. Which electron are we going to lose first? And hopefully you identified 3s1. Sodium becoming a +1 ion. If we rip off an electron, what's left behind is a +1 ion. The amount of energy it takes to do this is called the first ionization energy. And for sodium, that value is 119. Then the second ionization energy is the amount of energy it takes to remove the second electron, not from sodium solid, but from the sodium ion. So now if I remove the second electron, it's going to now become a +2 ion because now we've lost 2 electrons. And for sodium, that has a huge jump up to 1090. Well, why is that? Well, now we are going to pull from the 2p sublevel, and whenever we pull from the inner shell, you're going to see a huge jump up in energy. Okay? The third ionization energy is the amount of energy it takes to remove the third electron. So now +2 becomes +3. We have now lost 3 electrons. And for sodium, it's bigger, but it's not quite as big of a jump. And that's because now we've already pulled from the 2p sublevel. So further pulling from it is going to take more energy, but not as much of a jump as we saw the first time we start pulling from there. Okay? So, a couple things to take from this. Each electron that you remove, it gets harder and harder to remove the next electron. Successive ionization energies get larger and larger. As you keep removing the next electron, it takes more and more energy because we pull closer and closer to the nucleus. As I pull electrons from the 2p, there's less electron repulsion. The atom is constantly getting smaller and smaller, and the electrons are getting closer and closer to the nucleus. So every successive ionization energy, it takes more and more energy. 119, 1090, 1600, 2200. Look at aluminum. 138, 434, 656, 2767. Every ionization gets larger and larger. Taking an electron from the lower level is always much more difficult. Okay, if we look at magnesium, 1s2, 2s2, 2p6, 3s2. Which ionization will it occur that we start to pull from the inner shell? Well, magnesium has got 2 valence electrons. So the first ionization energy is going to pull the first valence electron. The second ionization energy is going to pull the second valence electron. Well, now magnesium has got no more valence electrons. So the third ionization is going to pull from the inner shell for the first time. We're going to pull from the second floor, which is magnesium's inner shell. And we predict that this ionization is going to be an astronomical jump. Do we see that in the table? Okay, so if I look at the table, magnesium, the first one is 176, the second one is 347, and the third one, 1848. We see a huge jump of over 1,500 to do the third ionization, and that's because now we're pulling from the inner shell. Once magnesium has lost its 2 valence electrons, it has now reached a full state of shells. That is the most stable configuration an element can ever have, and therefore it does not want to go away from that. Okay? The fourth ionization gets bigger, but it's not nearly as big of a jump, only 700, because we've now pulled from the inner shell. Pulling further from it is not going to have as big of a jump because now we've already decreased its stability by pulling from the inner shell. All right? Last concept on ionization energy, and also the last concept of this unit, and that is when we look at ionization energies throughout a period, for example, when I go from lithium to neon, if I look at the trend of the data, the general trend states that as I go across the period, Coulombic attraction increases, and therefore ionization energies will increase. That's something you have to know for the test. As I go across the period, the general trend is that ionization energies increase because the Coulombic attraction is increasing. Okay? However, when I look at the graph, it does show a steady increase up. However, there are 2 points in this graph that I see a dip, a drop. And that also occurs in every family, a drop and a drop, and a drop and a drop, and a drop and a drop. And when I look at those drops, it always occurs between the same 2 families, group 2 to group 13 and group 15 to group 16. Why do we see a drop here? Generally speaking, the ionization energies are increasing. When I start from the smallest member of the family to largest, we see an increase. But what's causing these drops or these dips? Let's take a closer look at it. The first one in lithium to neon is beryllium is in group 2. Boron is in group 13. So when I go across the family, these guys are next to each other. Beryllium has got the configuration of 1s2, 2s2. Boron is 1s2, 2s2, 2p1. So which electron am I going to pull from beryllium? One of these electrons from the 2s. I'm going to pull from the 2s. Boron, which electron am I going to pull from? Hopefully you said the 2p. Therefore, the question becomes, why is it easier? Boron, we see a drop. It's easier to pull the electron from boron. The first electron from boron, it's much easier to pull that electron than it is the beryllium. Even though the Coulombic attraction, even though boron has got more protons and therefore an increase in Coulombic attraction, why is it easier to remove boron's 2p electron than beryllium's? The answer is the 2p sublevel is farther from the nucleus than the 2s. And therefore, because the 2p is farther than the 2s, it's easier to remove an electron from the 2p than the 2s. The same thing happens between sodium and aluminum. Okay? Excuse me, not sodium and aluminum, my bad. It would be my fault. Magnesium and aluminum, my fault. Magnesium and aluminum, the same thing. Okay? We're going to be pulling from 3s versus 3p. It's easier to pull from 3p because it's farther from the nucleus, and therefore the ionization energy dips whenever we go to group 13 because we pull from an orbital that's farther from the nucleus. Okay? This secondary dip also occurs between groups 15 and 16. So let's take a look at this. Between lithium and neon, the example is nitrogen is group 15 and oxygen is in group 16. So nitrogen, 1s2, 2s2, 2p3 with 1 electron in each. Oxygen, 2p4. 2 electrons in one, 2 singles in the other. All right, now we are going to pull an electron from, in both cases, the 2p. However, for oxygen, does anybody want to take a guess as to which electron is pulled off of? One of the single occupied electrons in the 2p or one of them in the double? I'm going to assume most of you predict one in the double, and that is correct. So the question now becomes, we're pulling from the same orbital, so the distance isn't any different, but why is it easier to remove this electron in oxygen than it is to remove this one in nitrogen? Most commonly, students will say, well, if I remove this electron from oxygen, they all have 1 in each. So we get symmetry. However, symmetry arguments are not correct arguments. The reason is when I pull this electron from this orbital and remove it, 2 electrons in the same orbital repel each other. So by removing that electron, I decrease some of the repulsion in that orbital. And that decrease in that amount of energy that is being repelled there, by lowering that electron repulsion, that has a greater effect, or it trumps the fact that nitrogen has got 1 less proton in the nucleus. So even though oxygen has got 1 more proton and has a greater Coulombic attraction, the amount of electron repulsion that we're able to minimize by pulling that electron off causes there to be a dip in the energy. Okay? So I just want to talk briefly about these dips or these violations of the trends. Now again, for almost all the data that we're looking at a trend. So as I go through the family, the generalization in the trend is that when I go across the family, there's an increase in ionization energy. But what causes these violations or these exceptions to the rules? And this takes us to the next level of not regular chemistry, but honors. Being able not only to know the trends, but also to explain some of these violations of the trends. Okay? So here's the last concept for the unit. I know this is the biggest theoretical stuff. This is the stuff that for many of you are going to struggle the most. So please make sure you've listened to this lecture, and if you have any questions on it, please contact me. I'll be glad to go over it. But the quiz next week on this material, after you've studied it, should hopefully help gain, as you do more practice problems on these on the quizzes, should hopefully gain a better appreciation and knowledge for these types of harder level concepts. Okay? Again, thanks for listening, and that wraps up this unit on all the concepts of the unit.